Now, let us look at few electron gated quantum dots and how they satisfy the Divingenstow criteria to become successful and potential qubit candidates to host spin qubits, spin states of electron. The system that we want eventually is a few electron or precisely one electron gated semiconductor quantum dot. So, there are various geometries and various gate designs, various material systems available. So, let us start looking at first quantum dots on the gallium arsenide, aluminum gallium arsenide material system. Lot of progress in this field has been demonstrated using gallium arsenide, aluminum gallium arsenide material system. Later, recently, for the last 5 years or 10 years, most of the work has been moved on to the silicon based quantum dots for reasons that we will explain in this in the next after the next few slides. Okay. So, what you're seeing here is you have a etched region, that means the material system, in the material system the two dimensional electron gas has been etched out from these two regions, and this middle region which is labeled as mesa, you have two dimensional electron gas. There are two gates here. When you apply negative voltages on these two gates, you get a small confined or a quantum confined, electrostatically confined region which will host electrons, which will confine electrons. Okay. And this is a Coulomb diamond plot where gate voltage versus the source strain bias, and you can see there are a series of Coulomb diamonds and eventually these diamonds are fading away. You can also see that the size of the diamond also increases as you march down in the electron number. Remember, what we discussed is the electron number is stable in each diamond and it reduces by 1 when you go down in the voltage, in the gate voltage. Similarly, this another design where you have two channels, one is actually a sensor channel, other one is a dot channel. This is an interchangeable design. This is realized on silicon. Okay. There are few layers of gates here. This is an undoped system where you get electrons by applying positive voltages and you get barriers by applying negative voltages. Okay. So, this is a silicon dioxide system. You can get one quantum dot here, another one here, another one here. It's basically you have 4 dots in this one if you want, depending upon how you configure the voltages. Here also you can see that the diamond size as you march down reduces, eventually no diamonds are visible in this region. So, what happens is when you go down, the transparency of the system, because you are measuring the transport and you are increasing the you are reducing the voltage, or you are making the gate voltages more and more negative. So, the tunnel barriers which are defined by these voltages become more and more opaque, and the current is too low in these regions to measure. That is one region. That is one reason. Another reason would be that there are no electrons left in the dot. So, we do not know. Okay. So, we need to reach the few electron regime and we need to find the last electron and assign our qubit state to the spin state of that electron. That is our aim. But the question is, can we safely say that these two regions have no electron, or we are not seeing it because the current is too low, because you are measuring the transport, you are measuring the current through the system, or you are measuring the conductance. So, that is the big question. And this is a real life scenario where you have a bunch of diamonds, which is similar to what we have seen. The diamond size is increasing, and eventually you cannot measure any current. Current is the color scale here. As I mentioned, in this device, what you are doing is you are reducing one of the voltages on one of the gates. Okay, and the dot becomes too small. That is why the diamond size is increasing. The blockaded region, which is in the shape of a diamond, is increasing. And at the same time, you also make the tunnel barriers thicker. So, you start a dot with a profile with something like this. This is just a sketch, okay, just to give you a feeling what's happening. And when you go down towards the end, you make the dot smaller, but these tunnel barriers thicker, which connects the source and drain. So, current is almost immeasurable. So, what happens is the tunnel barriers become opaque in the fuel electron regime, and transport shuts down. And second thing is, transport is not a tool that you want to characterize or work with this devices, because transport means you replace one electron with another electron, but your state you have encoded onto one of the electron, and you don't want that electron to be lost. So, you just want to know whether the electron is there or not, and what is the state of that electron. You want to just to probe that aspect. You know, you are not trying to run a current through system. That is not your aim. If you try to run a current through system, it will replace one electron with another electron. That is transport, and you lose the state, right? So, that is not the aim. So, what we need is we just want to sense whether the electron is there or not, or the dot empty, is the last electron, are there any more electrons are there, what is the state of that electron. So, what we require is something like, we want to sense the electron, we need a electron sensor, or we need a charge sensor. That is what we need. Remember, when we design this dot, there are two extra electrodes or gates on either side. These 4 electrodes, when you apply negative voltage, will confine a small region where electrons are confined. Okay, that is the dot. But these two gates does not have anything directly to do with that confinement. What happens is, when you power this gate, when you apply negative voltages to this gate, you also will create a thin channel this side and another channel on the other side. But you need only one channel to sense that is the fact. You can have both if you want to do some specific measurement, but one is sufficient. And this channel is a thin constriction, in an otherwise a sea of electron, right? Now, the moment you apply voltage onto this, you are forcing all the electrons to go through this constriction, and that constriction is called a quantum point contact. And I am not going to go much in details of the physics of quantum point contact. It's a very interesting field, it's a very interesting device, very fundamental but very intriguing, but I am not going to go into detail. Okay. So, the point here is the conductance of this channel is actually quantized, or is highly nonlinear. Just take, let's maybe make that point more clear, that the conductance of this channel, voltage on one of the gates versus the conductance of the channel, that is quantized. The important point is not just the quantization, it is really steep, highly nonlinear. Very small change in the gate voltage means the field in the vicinity makes a large change in the conductance. So, you will be surprised to know that the electric field due to one electron or one extra electron, or the change in field due to change of one electron, can induce a large change in the conductance in the channel. Just like the charge on this gate which is set by the voltage, the charge on the dot also will act as a gate voltage for this channel. So, you know that when you cross a Coulomb blockade peak, one electron goes out or goes in, depending upon which direction you see. This is the real data where one electron goes out when you go from this regime to this regime, and this orange shaped trace here is the conductance of the channel, and you see that the conductance channel suddenly changes. It is giving a step. There is a slope to it, that is because of the direct coupling of the gate Vm to this channel, that is going to continuously reduce the current just like another voltage. But a sudden change in the electron number will act like a sudden change in the voltage, okay, on top of the continuous decrease, continuous reduction of the gate voltage. When an electron goes out, the channel see an increase in the voltage, or the voltage becomes less negative, so the conductance increases. That is the step that you are seeing. There is a small blip, a change in the conductance in the positive direction, that is due to the electron tunneling out. So, this aspect or this phenomena you can use to sense the electron in the dot. So, you in a normal transport you get a series of Coulomb blockade oscillation which correspond to the charging and discharging of the dot. But as I told, when you go to smaller devices, smaller dots, the tunnel barriers become thicker and thicker and thicker, and you cannot measure the direct current through the system. Then what you do is you use a sensor. This is quantum point contact, it's a charge sensor, to check whether the electron is there or not. That is more appropriate and more easier, and that is more robust, because the sensing the current does not really work in that regime. Okay. So, this is what you do. You just check for this blip, or derivative of that blip would be a peak. Okay. You check for that, see whether there are any more electrons left or not. So, what you do is, as you reach the fewer electron regime, you in parallel with the transport characterization, just characterize the system first, you also check whether you see these blips in sequence, and what you would see is the Coulomb blockade oscillations would stop beyond certain voltage, because then the barriers become so opaque you cannot measure the current. But you will see that these blips, or the derivative of those blips, those are peaks or dips, whichever way you take the derivative, that will keep on coming in regular intervals, and that is what is used as a sensor to see whether the dot is empty or not. Okay. So, this is a very, very important aspect. This is how you also read out, because now this is directly tied up with the one of the Divincenzo criteria, how you read out a state. Because when you when you make a qubit, when you reach the one electron regime, the dot is so small and the barriers are so thick, so you cannot use any other characterization, but you also need to sense. This is a sensor. It senses electrostatically whether the dot is there or not. Okay, and this is one of the Divincenzo criteria, whether you would be able to read out the state or not. But remember, this is a charge sensor, this is not a spin sensor, but our state is a spin state. So, I will get into detail how you sense a spin through charge. There is some mechanism, spin to charge conversion, which also we will discuss during the I think maybe in this lecture or the next lecture. All right. Okay. So, now if remember, in the previous view graph, what we saw is this picture where you have the dot on this side, you have the electron inside dot. When you make the gate voltage more negative, you push this level up, then the electron tunnels out. So, but the question is, this is a very slow process, right? You are sweeping the gate like in a slower rate, and at some point of time, electron has gone out. But you have no idea or no information on the time scales, or how long the electron took to tunnel out, how long the electron has stayed inside, how fast it tunneled out. You have no temporal information, because you are measuring the time average current through this channel here. That is what you are doing. This is your sensor channel, as we just discussed, but it's time average current. That is that the time scale is decided by the filter settings and other amplifier, the bandwidth of amplifiers. Usually they are very slow, like if you tens of millisecond is fastest you can do it. Okay, so that's what you do, but still you get some information, but not quite. So what you would really want is you want to measure the current in real time. That will give you in real time what electron is doing. Okay, so instead of measuring this through an amplifier, what you do is you hook up to an oscilloscope. Okay, then and you plot that as a function of time. What you see is you would see the ups and downs, the two state signals, because the sensor will have one state when the electron is inside, then another state when the electron is out. It's a bistable system, signal. So that's what you would see. So for this measurement, just to show that this sensor is working, what is done is you align the dot level with the Fermi level, so that the dot has the dot has probability to go occupied or empty, because these electrons can randomly tunnel back and forth because of thermal energy, which is given by the lead. Okay, so that correspond to the signal through the QPC going up and down depending upon how depending on the situation of the condition of the dot. So when the electron is inside, it is a higher negative charge or less positive charge, the current will be low. When the electron travels out, then the current will be high, current low, high, like that. Okay. So by analyzing this signal in the time domain, you can get information on how long the electron has stayed inside. For example, this width of this thing says, okay, the current was high for like say a few milliseconds. That means that much time the dot was empty. Here the longer duration here the current was low. That means you can say that much time the electron stayed inside. And of course, this is a random telegraphic signal, because the motion, the tunneling back and forth electron is decided by thermal energy. So it will be random in nature. So it's a random tunneling events back and forth between the dot and the lead. So we don't need to, this is perfectly fine. We don't need to worry about this, why the randomness comes, because the tunneling events are random. This is just characterize whether the sensor is working correctly or not. That's what we are getting. Okay. And for more details, we can refer this paper. There are more information that. Okay. So now the time scales of this measurement is again, or any measurement is actually decided by the bandwidth of circuit and bandwidth of amplifier. This is a simple DC measurement of the current, which is now taken in the time domain using an oscilloscope. Still, the amplifiers are same, everything is same, but what I am trying to say here is we can see the behavior of electron tunneling events of electrons in real time, which is an essential, very essential situation, because remember, one of the dimensions of criteria says you need to measure the state of system in single shot in real time. You have to measure. You get only one chance. So you need to know what the state of system is. Okay. So this technique is going to give you access to the time scales of this electron dynamics. Okay, in the dot. But this is kind of slow. This we need to refine, and this technique we need to refine, and we need to measure the time scales, or we need to sense the device, sense the dot in megahertz to gigahertz time scale to make sure that you can sense the device, you can get the information in a very, very short time without devising the system. Okay. And this real-time charge detection using QPCs as done on various dot designs. This is a dot which is defined by something called local oxidation. Anyway, the idea here is, again, you are sensing the current through this quantum point contact, which is designed, which are these channels, these bottlenecks here, and dot is here, and we are sensing the electron dynamics between the drain and the dot, and that is again giving you the random telegraphic signal. A similar story here also. So, what we are seeing is in all these measurements, what we can do is bandwidths of hundreds of kilohertz maximum that correspond to tens of microseconds, but not more. So, these measurements, whether the previous one here or the next one, these measurements are limited to like tens of kilohertz to maximum 100 kilohertz, but the dephasing time scales of some of the systems are in microseconds. So, you need to do this measurement much faster than the dephasing time scales of the system. So, we have to refine this technique to measure the state in much shorter time scale, and that is the take home message. So, that we will discuss how to do that in a minute, but this is another example where you can measure the charge configuration of a double quantum dot, there are two dots here, okay, using a charge sensor. This is the conventional charge stability diagram for a double quantum dot, where you see the honeycomb shaped regions, where at these corners of this honeycomb you see currents. That is that you got by measuring the current through the quantum dot, direct current through the quantum dot. This is the conductance of the double dot, okay, as a function of two gate voltages. But what you can do is you can get the same information if you sense the charge states of the system, either this one or this channel. So, the current through this system, this channel here, is going to sense the charge, not the current through the dot. It only senses the occupation of the dot. It does not sense the current through the dot, because a charge sensor, it is not a current sensor. Okay. It will tell you that the dot is occupied or not, or how much is the average charge on the dot. That is what it is going to tell you. Okay. So, that is plotted in color scales. You can see that the color is changing here, that depends upon the average charge configuration, but it is going to map exactly the same honeycomb, but slightly in a slightly different perspective, because here you can see the color is same, and the color is suddenly changing whenever you cross any of these edges of the honeycomb, any of the honeycomb, because it is sensing the charge. When you cross the edge, the charge is changing. There is no current when you change the gate voltage in this direction. There is no current flowing through, but you are changing the charge configuration. Okay. You are going from Mn to Mn n plus 1 to n. So, the overall charge of the system has changed, and this is sensing the charge, not the current. So, as far as sensor is concerned, you can see that the average charge of the system is now different. So, it is going to show a different current. That is true for whenever you cross any of this boundary, you will see that. And if you take the derivative of that, you will get something like this lines, okay, or peaks. If you take the derivative of this, you will get lines like this. This is another device where what you are measuring is the differential conductance instead of the current, and you can see the charge stability diagram. Finally, your dot is empty. This is this region. If you measure transport to direct transport through the system, you will get this one. If you measure the current, if you measure current through sensor or the conductance sensor, you will get this one. Okay. So, you see the current signals are there only at these corners, but you can see all other boundaries of the honeycomb when you do a charge sensing, because charge is sensing the change in charge configuration. Current is sensing the current through device, but current through device is present only at these corners, but charge configuration is changing whenever you cross any of this boundary. So, the sensor is sensitive to that. So, that is the advantage of a charge sensor, because if the overall charge is same, it will not sense it. But the idea here is, if you say you are going between these two states 0 1 and 1 0, that means you are taking one electron from one dot and putting another dot. But when you do this, no change in the current, That is why if you, the current through system will not show you any change, but the charge, overall charge is overall charge is same, but the when you are what you are doing is you are taking one electron from this dot and transfer other dot. So, the effective charge seen by this channel is different now. It is higher, it is lower here. So, this is going to give you a change in the color, or when you take derivative you will see a line. Okay. So, the sensor is sensitive to any movement of electrons in the vicinity, charge sensor. It does need to be a movement through the entire circuit, then only you get a current through it. But any rearrangement of the charge configuration, the sensor is going to sense. That is the advantage, and that is it is very important, because when you work with these qubits in these electron systems, what you have is only rearrangement of electrons. You don't have a current running through system. So, current is not an option. Measuring current is not at all an option. The only option to you is measuring the charge state, and that is why these charge sensors are so important. Okay. So, what we have discussed so far is we can form a few electron quantum dot system in these materials to host qubit, and when you make these devices to reach the few electron regime or one electron regime, the dot becomes so small and the tunnel barriers become so opaque, so thick. So, you cannot measure the current through system, and measuring the current through system is not also an option. So, you need some kind of a sensor to sense the electron is there or not. It is a charge sensor, and the quantum point contact, which is defined, or it is realized by having an extra gate on the side of the dot, which will provide a thin channel in combination with one of the dot gates, will work as a sensor, and you can sense any rearrangement or movement of electrons within the dots using the sensor, and which is one of the major which satisfies one of the major dimensions of criteria to sense the or read out the state of the system. That is what we have so far.